Hey everyone! In this video, we're going to look at how the Flipper Zero can interface with devices that support SPI. Many devices support SPI, such as SD cards, temperature sensors, and flash memory. I'll be using flash memory for this video, and we'll dive into the technical details of SPI and also look at some code. Let's get started. SPI, Serial Peripheral Interface, was created by Motorola in the 80s. Many people have taken it and extended it over time. Even this flash board redefined how the D1 wire works. For this video, we'll be focused on the basic 4-wire implementation plus power and ground. Let me start by removing all these wires, and then we can add them back as I explain what they do. This first wire goes to pin 4 on the flipper. It's chip select. And the chip select wire goes low when the flipper wants to talk to the device that's on the other end of that wire. Pin 5 on the flipper is the serial clock. The clock alternates from high to low, and it's controlled by the main device, which is the Flipper Zero. We'll come back and talk about how the clock is used in a moment. Next we have pin 2, which is main out sub in. And again, the flipper is the main device, so it's its output wire. This output wire is used to send commands to the device, request memory addresses from that chip, send data that it wants to store, that kind of stuff. So it's data in from the perspective of the chip, but it's main out sub in. Next we have pin 3, which is main in sub out. Again, the flipper's that main device, so it's input to the flipper and it's data out from the device. So this is where the flipper is going to read information from that device and also obtain status information from that device. Pins 8, 11, and 18 are all ground. You can use any of these pins to go to ground on the device. And finally, we're using pin 9 for our 3.3 volt power for our device. SPI doesn't define the power, so it is possible that the device you're using uses pin 1 for the 5 volts power. Now let's take a look at the Flipper Zero sending a request for the chip ID. At the top, we see pin 4, chip select, goes low. So that indicates that the other pins are meant for communication between the flipper and the device on this wire, which is that flash memory. Next, we have the clock. And again, the flipper controls those clock transitions. And for the flipper's external SPI, it's configured where the clock is low when it's inactive, and the data is valid on the clock's rising edge. SPI has different ways that clock can be treated, but for the flipper's external SPI, this is how it's configured. Next, we have the MOSI, which was our output from the flipper. And if we read the first byte, when that clock goes high, we get 10011111, which is the instruction that requests the chip ID. And while that memory is replying, it ignores whatever data we continue to send. Finally, that bottom wire is MISO, which is our flipper in. And that first byte isn't used since the chip doesn't know what we want. But the second byte is replying to our request. And so we get 11101111, which represents the WinBond serial flash component. So we sent 9F and we received EF and then 4016 for the device ID. On the Flipper Zero, we'll open the SPI Memory Manager, choose Read, which requests the chip ID, WinBond serial flash, and then there's our model. And then we'll do Read, which starts reading different addresses off of that chip. Back in our logic analyzer, let's zoom into that request for the chip ID. And we can see 9F EF4016. Next, let's zoom out, and I'll zoom into some of the memory read commands. So this time you can see we're sending a request to read memory, which is instruction 03. And then that address that we want to read from is 00 WS2812B and then that memory contents is 48, 65, 6C, 6C, 6F. And if we look down at the ASCII table and we find 48, we see it's a capital H. And then if we look for 65, we see it's lowercase e, and then L, L, and O. So that's the greeting I chose to store at address 000100. And again, you can store any data you want on the memory chip. Now let's look at the code for the Flipper 0. Lines 36 and 38 are critical, which is frui hal SPI bus handle init when you start, and then dinit when you're done. I recommend you just put this at the beginning of your entry point function. I forgot to do this once, and I spent hours debugging. A few times your app will actually work and you'll read the data, but most of the time you won't. So just remember to do this. All right, once we've initialized our SPI bus handle, then we do line 17, which is frui hal SPI acquire, and that acquires the bus. After we've acquired, we can go to line 19, which is frui hal SPI bus TRX, which stands for transmit and receive. It takes the SPI, a buffer to transmit, a buffer to receive, how many bytes are in that buffer, and then the timeout. And then once we're done sending and receiving, we do line 32, frui hal SPI release. So this works okay, but on line 14 and 15, you can see we had to use 10 bytes for our command that we're sending and 10 bytes for the data we're receiving. And then on line 20, we had to add 4 so that we skipped those first 4 bytes that were the command we were sending and the address that we were asking for. So here's a second version of the program. Again, on line 39 and 41, we have that SPI bus handle init and dinit. Don't forget that. And then line 18, we do the SPI acquire. This time on line 20, we do a frui hal SPI bus TX, and we give it the buffer we want to transmit. And then we have and at the end. And then another TX, and we give it the next buffer we want to transmit, which is our address. And then and then we have the frui hal SPI bus RX for receive, and we give it the buffer we want to receive in. Now on line 23, we no longer have to add 4 because we're writing direct to the beginning of that data response buffer. And you can see that lines 14 through 16 are now using only half the amount of memory on the Flipper 0. Once we're all done, again, we call that frui hal SPI release on line 35. So I've opened the Flipper CLI. We'll go ahead and run log. And then over on our Flipper, we'll go ahead and run the program. And looking at those red logs, you can see that both V1 and V2 were able to extract the message hello from our flash memory. Hopefully now you know the basics of SPI. In a future video, I'll go more in depth about how we can tweak the external SPI to control some addressable LEDs. And we can also look at the external CC1101 radio. Please like and subscribe. And thank you for your time. Don't forget to join my Discord server. I'd love to hear about the projects you want to create.